In this video, we are going to have the definition of normal subgroups and quotient groups and examples for normal subgroups also. First, we have the definition. A subgroup N of a group G is said to be a normal subgroup of G if for every G in G, N in N, G in G inverse belongs to N. This product in this G should be from capital G and N should be from capital N, and this must hold for all G in G and N in N. Now we are going to have another description for the same definition in terms of sets. That is due to the definition of G capital and G inverse is given by this. And so a subgroup N of G is said to be normal in G if for every G in G, G and G inverse is contained in capital N. Now we have these few examples. If we have G to be the set of group of integers under addition and N to be the set of multiples, we know very well that this collection, which is a collection of all multiples of N, so this is already known to be a subgroup. This is a subgroup of Z and R plus. So this subgroup is normal in G. Later we will be seeing a result which will state that every subgroup of an abelian group is normal in G. So based on that only we have this to be an example for normal subgroup in a group G. So group is the group of integers under addition, and N is all multiples of N, the set of all multiples of N which forms a group under addition. The next example is S3, which consists of epsilon, alpha, beta, gamma, delta, theta, where we know already that epsilon, alpha, beta, gamma, delta, theta, they stand for this. Then if we consider this collection epsilon, delta, theta, then that is a subgroup known already, and that is the only normal subgroup in G. This is the only normal subgroup in S3. And the next one is quaternion group. If you consider G to be this quaternion group, and all the subgroups, if you consider all of them are normal in G. And for this we can we are going to have in the following lemmas the conditions for subgroup N to be normal in G. So one of the criteria can be used, or even the definition can be used to check whether these examples are correct. Now first lemma states that N is normal in G if and only if G and G inverse equals N. We know from the definition that G and G inverse is contained in N. Here equality should be true. Whenever this is true, we can have N to be normal. So this is one of the criteria for N to be normal in G. So if we assume that G and G inverse to be equal to N for every G in G, then definitely G and G inverse is contained in N. Therefore, by the definition, this is the definition, the alternate definition, G and G inverse contained in N. So that is true. So we have by the definition N is normal in G. Now suppose that N is normal in G. Then you have to show that G and G inverse equals N. So again by the definition, one way we have the inclusion to be true. Next we consider G inverse N G. If we consider this, we can rewrite this as G inverse N G inverse the whole inverse. So again use the same to see that G inverse NG is contained in N. Now since G inverse NG is contained in N, be make use of this to conclude that this G inverse is sandwiched between N and of course N. So you consider now N, rewrite that as E N E, because N has E, you can rewrite in this way, and replace your G by GG inverse, and again this E also identity element, and group it like this. And because of this, this is the whole lot is contained in N because of this. So you have this, and because of this, you have G and G inverse to be contained in N. So what happens? This G and G inverse is sandwiched between N. So you have N and N itself. So you have, there is no other go, N should be equal to G and G inverse. Next we have the lemma which states that the subgroup N of G is normal in G if and only if every left coset of N in G is a right coset. Every left coset should be a right coset. Now if N is normal in G, then for every G in G, G and G inverse equals N. This is what we proved in the previous lemma. Now if we consider G and G inverse int G, this if we consider, then that is nothing but NG. Now from here you club these two, you get E. So G N E, which is same as Gn, is equal to Ng. So that means a left coset of N in G is a right coset of N in G. So Gn equals Ng proves one way. Then for the converse part, let every left coset of N in G be a right coset of N in G. Then for G in G, Gn being a left coset must be a right coset. So suppose Gn is equals Na. This is a left coset of N and this is a right coset. Now actually we are going to prove that this Na is nothing but Ng. This Na is nothing but Ng. So from that easily we will have G and G inverse to be equal to N. Therefore by the previous lemma we can conclude that N is normal in G. So we consider now, see our aim now is to show that this Na is nothing but Ng. So for that we consider G, which is Ge. You can rewrite that, and this E belongs to N, so we can have this step G equals G belongs to Gn, but Gn is nothing but Na. Now we also have G being rewritten as Eg, that belongs to Ng. So you have G to belong to this right coset, G also to belong to right coset Ng. We know already that any two right cosets are disjoint or identical. So here they are not disjoint because G belongs to Na as well as Ng. So we have Na intersection Ng being non-empty. There is no other go, Na has to be equal to Ng because any two right cosets are either disjoint or identical. So if Na equals Ng, from here we get Gn equals Ng. So by 1, that is we make use of this. So this in turn implies that your Gn G inverse, your job is to show that N is normal. So from here we conclude that Gn G inverse equals N for every G in G, and therefore N is normal in G. So this by the previous lemma implies that N is normal in G. N is normal in G. In the first one we have just G and G inverse equal to N, implying N is normal in G. Here every left coset is a right coset. In turn gives G and G inverse to be equal to N, and hence your N is normal in G. Then next lemma, a subgroup N of G is normal in G if and only if the product of two right cosets is again a right coset. Now first we shall assume that N to be normal in G. Then we shall take A and B in G. So if we consider Na into Nb, product of two right coset, then if we group like this, then this left coset will be a right coset by the previous lemma, as N is assumed to be normal in G. So this is what we get. So this in turn implies Nn AB, but this Nn is nothing but N. When we consider this as sets, they are equal. So you have N to be equal to N. So we have product of two right coset to be again a right coset. Now for the converse part, we shall assume that product of two right cosets is again a right coset. So for that, instead of considering NA and NB, we shall consider like this: NA inverse equals NC. Name that as equation 1. Now you consider E, that can be rewritten in this way because AA inverse is identity element, so we can write like this. And because this is of this form, NA inverse, an element in this collection is only of this form, so it has to be there in NA inverse, which is taken to be NC. So you have E belonging to NC. Now again rewrite your E as E into E, and that obviously belongs to NE. So again, like in the previous case, you have in the right cosets NC and NE, E to be a common element, but any two right cosets are either disjoint or identical. Here they are not disjoint, so they must be identical. So we have this is NA inverse. NA inverse to be equal to NE, or you can even have N1A. A particular case, you have NA inverse, N1A, N2A inverse equals N3. See, we have as sets only these two to be equal. This does not imply that NA inverse equals some N. Of course, we have when we have this G to be commutative, this one to be true, but not even if it commutes, then also you will have only N square. We cannot have N square to be equal to N, excepting for N to be E. So we have this to be true. So this in turn gives N to A inverse to be, we are pre-multiplying by N1 inverse, so you have this. So you have N to A inverse belonging to N. For every AN, this is true for every AN G. This is true for every AN G. So you have from the definition we have N to be normal in G. So in the previous one, the first lemma is used, and in this we make use of the definition to prove the converse part. Next we have this theorem: if G is a group, N is normal in G, then G mod N is a group, and that is called quotient group. So let N be normal in G, and let G mod N, this has to be read as either G by N or G mod N is the correct way to read it. G mod N is the collection of all right cosets of N in G that we have here. So this is the notation mathematically. This is how we denote it. Now to prove that this is a group, some product is to be defined on it. So we shall define on G by N the product in this way. Now under this product we prove that G mod N forms a group. So for that, closure, associativity, existence of identity, and existence of inverse, they all should be true so that we can conclude that G mod N is a group. Now first we consider two elements, say X and Y in G mod N. Then X can be written as, because it's a right coset, like this we can have, and Y to be NB, where A and B are in G. Now if we consider the product XY, it is NA NB. Now because N is normal, this we had already. Because N is normal, we can rewrite like this. So this is again a right coset. G mod N being the collection of all right cosets, this has to be there in G mod N. So that proves the closure property. And for the associativity, we need to consider three elements, say X, Y, Z, so that your X, Y, and Z will be NA, NB, and NC respectively, with A, B, C in G. Now if you consider X dot Y dot Z, then this is what we have. And this is again NAB, and you have this being rewritten as N A B C. So all these are possible only if you assume N to be normal subgroup. So then again, these elements being in group which is associative, so we can interchange the bracket, so you have this. So that is because G is associative. And from here, because N is normal, again you have this step, and again normal, so you have N is normal, so you have this step, and this is nothing but X, this is Y, and this is Z. So we have associativity also to be true. Now we are going to have this N, which is NE in G mod N, acting as the identity element. So for that we shall consider some X in G mod N, so that that X can be written as this right coset NA, where A belongs to G. Now if you consider X into N, we have NA into NE, that is NAE, but A into E, E being identity element, is NA, and that gives back your X. So similarly, you can have Nx to be equal to X, and therefore we conclude that Ne is the identity element. Ne is the identity element in G mod N. Now for the inverse, we'll have to consider an element in G mod N, and if you consider Na inverse, that is also present in G mod N. Because once you have this to be a member of G, automatically this will be a member of G mod N. So when we consider the product Na into Na inverse, which is because N is normal, you get this. So that is the Ne, which is the identity element which we have mentioned earlier. So naturally this must act as the inverse of this. So you have a existence of inverse element in G mod N also. So this G mod N is a group, and that is called the quotient group or factor group of G by N. Now if G is a finite group and N is normal in G, if we have finite group, then order of G mod N is order of G by order of N. Now we know that because G mod N is the collection of all right cosets, the number of right cosets of N in G is nothing but the index of N in G. This is explained in section 2.4 under Lagrange's theorem. So the index of N in G is the number of distinct right cosets of N in G. Therefore, order of G mod N is nothing but index of N in G. But again, from that section 2.4, we also know that if G is finite, we can have the index as given by this formula. Index of N in G is order of G by order of N. So we make use of this 1 and 2. From that we conclude that order of G mod N is order of G by order of N. So when G is finite, this formula explained already in section 2.4. So from that we conclude that order of G mod N is order of G by order of N. So in the next video we will have few results on normal subgroups. Thank you.